Hi everybody, welcome back to Happy Little Diodes. I learned recently about the existence of 80k upgrades for ZX Spectrum 48Ks. Having a look around, I saw that one was sold by East London Robotics called an SP80. There are some photos available online, so I thought it's about time we had a reverse engineering video. So let's see if we can figure out how this thing works and build one ourselves using a breadboard. I've even bought myself a tiny little cheap and cheerful logic analyzer so we can see how it works when we're finished. This is the January 1984 edition of Sinclair User. Inside here there is a full-page advert for East London Robotics products. They sold a 48k upgrade for your 16k Spectrum for £23. There's an issue 1 and an issue 2 version of the upgrade. What we're interested in is the other product, which is the 80k upgrade called an SP80 paged memory extension for 46 quid. The advert tells us that it gives an extra 2 memory banks each of 32k to give a total of 80k of RAM. You can switch between the two 32k banks using software instructions within your program. They also offered a fit and test service for £3 or by £7 if you send it in by mail. Let's look at the shopping list. We have a 48k upgrade, which is £35 for an issue 1 or £23 for an issue 2 Spectrum. Similarly, the SP80 upgrade is £50 for an issue 1 and £46 for an issue 2. It costs a little bit more for the issue 1 version because it had to come on a daughter board such as this one. I believe this is an SP80 upgrade designed for an issue 1 Spectrum. But we don't need to be messing around with the issue 1, let's do the issue 2 upgrade. Thanks Steve for providing these photos which has made this possible. Here's a view of the entire mod. It's all happening pretty much around the multiplexer chips in the top middle of the board. Now zooming in, this does look like pretty much a normal 48k board chipset, but there's one additional chip over the top of IC26 in the top right there. That's the one with the resistors on top of it. So when you bought the kit, you must have been given the upper RAM chips and these 5 chips, all pre-soldered together with these wires just to plug in, and away you go. The goal of this video is to explain how this works from the bottom up. In order to do that, we need to understand what the memory map of the ZX Spectrum looks like and how it addresses those different parts of memory, especially the upper memory, which is what we're most interested in with this mod. So let's get into it. Here we have a vanilla issue 2 Spectrum which has just had a service and is now sitting in my collection. This is already being upgraded to 48k, so I'm going to need to desolder a couple of chips and socket them in order to carry out the mod when I come to reverse engineer it, but for now let's leave it untouched and go through the memory map. The first bit of memory in the Spectrum isn't random access memory, it's read-only memory. That's our ROM chip, or it's kinda like the operating system. It sits in the top right of the board here and resides on a chip with 28 pins. The next bit of memory is the lower memory, so-called lower, and this is made up of 8 16-pin chips, 4 116 chips to be precise. And finally we have what's called the upper RAM. This is the extra 32 kilobytes of RAM which you get when you upgrade your 16k Speccy to a 48k Speccy. These are also 16-pin chips and these are 4532 chips. Okay, easy so far. Let's break it down further. The ROM occupies addresses 0 to 16k, so the first 16 kilobytes of memory within the Spectrum is read-only memory. Next up, the lower memory occupies addresses between 16 and 32k, giving us our 16k of usable memory. This is what's called contended memory because the video data is also in there, so the board had to be designed carefully to allow the user to access that memory without interfering with the video display output. Finally, we have the upper RAM occupying addresses 32 to 64k, giving us the 32 kilobytes of extra RAM which we get when we upgrade to a 48k Spectrum. So here's a real quirk about the ZX Spectrum. The capacity of the lower RAM is 16 kilobytes, and that makes sense because we have 16 kilobytes of memory to play with. The capacity, however, of the upper RAM chips is 64 kilobytes, so why can we only get 32 kilobytes out of it to play with? Well, this is the first clue as to how the 80k upgrade is going to work. Let's talk about addressing. Starting with the ROM chip because it's the most simple example, here it is. As I mentioned, this has 28 pins, which is loads of pins, especially compared to the RAM chips. Let's break it down. This ROM, as I mentioned, has 16 kilobytes of memory, or 16,384 bytes of memory. So we need to be able to address this many memory locations. That doesn't mean the highest address is 16384, we need to subtract 1 because the addresses start from 0, meaning our highest address is 16383, or 3FFF in hex. Let's convert that to binary, and we get 0011111111111111, which I'm sure you were all thinking. How many ones is that? It is 14 ones. 4, 8, 12, 13, 14. That means we need 14 address bits in order to address every location in this ROM chip, and that corresponds to address lines A0 to A13. I've started explaining addressing with the ROM because there are so many pins, it's quite simple to do. The Z80 here on the left also has loads of pins, meaning it can have one pin for every address line, from A0 to A13. Well, okay, to A15, but they're not relevant to this part of the explanation. There's a corresponding pin on the ROM chip for every one of these address lines in a slightly more mixed up order, but there they are. So when the Z80 wants to access some information from a particular address within the ROM chip, I'm simplifying here by the way, but it sets up the address pins to represent the address it's interested in. The ROM receives this address and it spits out the data on the data bus. Remember, it's an 8-bit computer, so there are 8 pins to represent the entire data bus and the byte of data which gets spat out. Okay, how are we doing? Is everyone still with me? Good. Let's move on to the lower RAM. So this is much different to the ROM chip. We have 8 individual chips, each with only 16 pins. You might be thinking, well, there's 8 times 16 pins there's plenty there to do some addressing, but it doesn't work like that. All of these chips are identical, each one contributing 1 bit of data to the 8-bit data bus. In fact, with the exception of the 2 data pins, all of the other 16 pins on all 8 of these chips are joined together. Let's take pin 5 for example, which is A0. Pin 5 on any one of these chips will measure continuity, basically zero resistance, to pin 5 on any of the other chips. So now that we know that they're all basically identical, let's zoom into one of them so we can talk about how it is addressed. You might be thinking that this chip isn't identical to the others because it looks different. Well, this board's been repaired. There must have been a bad RAM chip at IC13, which has been replaced by an equivalent. So similar to the ROM chip, we have 16,384 bits of data inside this chip. Not bytes, just bits, because like we said, each chip contributes 1 bit to a data byte. And also, just like the ROM chip, we need 14 address bits, A0 through A13, in order to address all of these locations. Now, given that these chips need 3 voltage supplies as well as ground, and they have 2 data pins, that means we need 20 pins to address it directly like the ROM chip, which isn't possible. This means the chip designers have done something clever, which we're about to go through now. These chips actually have 7 address pins. I've marked them here A0 through 6, although the numbering doesn't really matter. When the chips are addressed, they're first fed 7 address bits of the location which the CPU or whatever is interested in. Then that's where this pin comes in, which is called RAS, or the row address strobe. And when this is set, those 7 address bits are stored temporarily within the RAM chip. Then the 7 address bits all change again to represent the other half of the address which we're interested in. Then another pin comes in called CAS, or column address strobe. When this is set, then the RAM has received all 14 bits of the address which we want to read or write to. The fact that they're called row and column kind of gives away that it's a matrix structure, and what we're doing is giving it a row and a column of the quote table which we want to read from. Here is a microscope shot of a 4116 chip, and you can see that the bulk of the space is occupied by a big matrix of cells which contain our data bits. This shot is used with permission from Ken Sheriff. Check out his blog for more stuff like this. And then the data bit comes out. All 8 of the chips do this simultaneously, and we have a data byte, and everyone's happy. Okay, everything's pretty clear so far. I think we're building it up step by step. Nothing should be too confusing by this point. So let's charge on to the upper RAM, and similar to the lower RAM, or well, identical to the lower RAM, each of these chips contributes 1 bit of data to our data byte. And also, the same as lower RAM, all of the pins with the exception of the data pins are linked together. So there's A0, you would measure continuity between any two of those pins. Alright, easy peasy, let's zoom in. That's where the similarities end. Now we have 4532 chips, rather than the 4116 chips that we saw in the lower RAM. Let's shift it over to the side to make room for a bit of jargon. Are we expecting 16,384 bits of data in here like the lower RAM? No, we're not. We're expecting 32,768 bits because this is our 32 kilobytes extra memory, which makes our 48K spectrum. But no, that's still wrong. This chip actually has room for 65,536 bits of data, which is 64 kilobits. What does that mean? That means we need to address locations from 0 to 65535, and 65535, which is FFFF in hex, is 111111111111111 in binary. Which means this chip must be designed with some kind of mechanism to feed its 16 address bits. This is good because we know how this works already from the lower RAM. We have A0 through A7 initially, there's an extra address bit there on pin 9. By the way, the reason this has more pins available is that this only needs 1 voltage supply, whereas the lower RAM chips needed 3. That frees up an extra 2 pins. So here we go, we have RAS and CAS just like the lower RAM, and those work in exactly the same way. Once we've latched in the first 8 address bits, we set RAS, and then we latch in the remaining 8 address bits, and the RAM has its full address, 16 bits. It then spits data out on the data pins. These two are linked together, by the way. And once again, everybody is happy. Although we do have a question about this 64 kilobytes of capacity in the upper RAM, as opposed to the 32 kilobytes which we have available to us. So what's going on there? We need to take our journey over to another part of the board and understand how the 2 halves of the address, which is fed to the memory chips, is generated. And at least on this issue 2 board, this is where that happens, ICs 3, 4, 23, 4, 5 and 6. And the function of these chips is fairly simple. ICs 3 and 4 are called multiplexers. These are responsible for feeding the address in 2 halves to the lower RAM chips. And then we have ICs 25 and 26, which are the upper RAM multiplexers. These do the same thing for the upper RAM. We don't need to go through what the lower RAM multiplexers are doing, it's basically the same as what the upper RAM multiplexers are doing. So let's start with this one, IC25, we'll call it MUX1. I'll represent what's going on the left and right in terms of in and out. So it's receiving address lines A0 to A7, which is half of the address bus. And subject to some timing conditions, it first outputs, let's say A0 to A3, and then that's locked in using the RAS signal, and then afterwards it outputs A4 to A7, and that's locked in using the CAS signal. So that's half of our address, which is accounted for using IC25. IC26 is in parallel doing basically the same thing, but we need to represent it a little bit differently. So again, with in on the left and out on the right, let's see what's happening. These chips receive their inputs in pairs. So let's say it receives A8 and A9 as one pair, 10 and 11 as another pair, 12 and 13, and then 14 and, well, something in the final pair. You would expect that to be A15, allowing us to address the 64 kilobytes available in upper RAM, but that's not the case. It's been designed with a 32 kilobyte upper RAM, so A15 isn't used. And again, subject to some timing conditions, the first of each of these pairs is output. Those 4 address bits are latched in using RAS, and then the second of each pair is output and latched in using CAS, giving the 16-bit address which the upper RAM needs to spit out its data. So what's going on with this unknown input? Well, let's turn our attention back to the upper RAM chips. As we mentioned, the upper RAM chips have capacity for 64 kilobytes, which we aren't using. Now here comes the prior knowledge. 32 kilobytes of the memory in these chips is, quote, bad. And this sounds disastrous, doesn't it? But it's a known condition, some kind of problem with the manufacturing process, but they were all tooled up and Sinclair must have said, hey, we'll order loads of them on the cheap, given that the chips are marked to tell us which 32 kilobytes of each RAM chip is bad. And this is great because they could design the board to take that into account and ignore the quote bad half of the RAM. Picking up where we left off then with the upper RAM addressing, we'd established that there are 16 address bits going into this chip, giving us 64 kilobits of memory. Here's what happens. First of all, A0 through 07 is provided. Let's say that's those first 4 ones in our address there on the right. This is locked in using the RAS signal, as we already know, and then the expected remaining 8 address bits are provided. But we established that A15 isn't used here. So let's think about this input. What if it was set to 0? Well, we still have A0 through 14 to play with, which gives us 32 kilobits of available memory, or gives us 1/2 of the memory available in this chip. What if it was set to 1? All we're doing there is essentially switching to the other half of the memory in the chip. So this input on pin 9 with question marks is really key. This is what we're going to use to select the good half of the memory. So let's lock it in with CAS, and we can see that we've locked in the other half of the address bits I've highlighted here on the right, leaving out A15, or whatever we want to call it now. So the value of this either has to be 0 or 1, and this is given away by the markings on the chip. If you see a 3 at the end of this Texas Instruments chip, we know that the value of this input needs to be 0 volts. That means that this address bit is always fixed at 0, and we have reduced our RAM capacity from 64 to 32 kilobits per chip, giving us 32 kilobytes of upper memory, and potentially 32 kilobytes of unused memory. And finally, how do we feed this 0 volts through to our upper memory? Well, we know it comes out of the MUX chip up here on the right hand side there. Depending on the kind of upper memory we have a 1 or a 0 coming out, depending on which half of the RAM is bad, which means we have 5 volts or 0 volts coming out. And that can only mean on the left hand side we have to feed it 5 volts or 0 volts. This wasn't a surprise to the designers of the board, and this is allowed for with a link. You can see it in the top left here of this section next to the ULA. There it is. So depending on the upper RAM which was fitted, this link was made to 5 volts or 0 volts. On this particular board it was set to 0 volts because the upper RAM chips had a 3 marked on them. If the particular batch of chips were the other kind with a 4 marked at the end, as you can see here, there's the 4, that means that we need to provide a 1 or plus 5 volts into our mystery address pin, and the link is made as shown here to 5 volts. In the subsequent issues of the ZX Spectrum 48K, more links were provided, but they still allowed for this. Here we can see we have a TI link made, meaning we have Texas Instrument chips, and there are 2 links here. One is just marked 3 and one is marked 4, which corresponds to the markings on the chips. The other links on here marked OK and L and H, which are made on this board that I managed to dig out, were to be used if the upper RAM chips were from the manufacturer OK, and these particular chips were marked with an L or a H, and the corresponding link had to be made, which just about covers all of the possibilities for upper RAM. Okay, well, now we understand how the memory in the ZX Spectrum 48K is addressed. It's given us a foundation to understand what's going on with this mod and how we can get 80K out of our Spectrum using only one additional chip. Now might be a good time to pause the video and get a cup of tea before we launch into the full-on analysis of how this works. Okay, are you ready? Let's go. The mod is mostly affecting IC24 and IC26, with one wire there attached to IC23. Here's the part of the schematic which relates to IC23 and 24. We'll keep that there because it will be handy. IC24 contains 4 NAND gates. There it is. IC26 is one of our multiplexer chips that we just learned about. We don't need to see the insides of that for this explanation. We just need to know it's a 74LS157. Finally, we have a new chip which is piggybacking on top of IC26. This one contains 4 NOR gates. Looking more closely at IC24, we can see that some of the pins aren't in the socket. So let's mark them on the diagram. We'll mark them in blue. Pins 1, 2 and 3 on the left hand side aren't plugged into their sockets, and on the right hand side pins 12 and 11 aren't plugged into their sockets, so let's mark that as well. What about IC26 and the new IC which sits on top? Let's take a look at the left hand side for a start. We can see that pins 2 and 13 are joined over the top of the chip. I can also see that pin 5 of the new IC is connected directly to pin 5 of IC26. This is A7 of the address bus. I can also see a resistor coming off pin 1. The resistor, by the way, is of value 470 ohms. Let's have a look at the right hand side of this piggyback situation. Oof, what a mess. Okay, what can we see here? I can see that the resistor is connected to an LED which connects to pin 14, which is the voltage supply to the new IC. The new IC also gets its voltage from the voltage supply to IC26. It's piggybacked straight on top of it. I can also see that pin 1 is connected directly to pin 12, which is one of the inputs to one of these NOR gates. And I can see that pin 1 is connected to pin 10 of IC26. This is our very interesting input. This would correspond to A15 like we just learned. Basically this is going to select which half of the upper memory is currently active. I'm going to call it bank. And it's obvious now that the LED is designed to show us which half of the upper memory is currently active. Cool, that's our master output of this mod, and that's the most interesting signal. Can also see that pins 10 and 11 are connected via a 3K9 resistor. And finally, I can also see that pin 9 is connected to pin 11 of IC26, which is A14 of our address bus. Now we need to start tracing where these green wires are going. Starting off here, pin 6 of our new IC corresponds to the read signal, which is active low. That's connected to pin 5 of IC24. Pin 4 of the new IC is connected to pin 1 of IC24. We don't have a name for this yet because this is just an output of the new IC and it's going into an input which was previously unused of IC24. There's another wire here going to IC23, goes to pin 2 of IC24, and it just so happens that this is MREC. This is active low. This is a signal which sets when there is a memory request happening from the CPU. This might mean we're trying to write to or read from memory. Still looking at IC24, pin 3 doesn't have any wires attached to it and it's not in the socket, so let's assume it's going underneath the chip and connecting to pin 12, which also isn't in its socket. Pin 12 incidentally does have a wire attached to it and it goes to pin 8 of the new IC. Again, we don't really have a name for this. I'm going to call it flip-flop trigger. If you trace it from pin 8 of the new IC, we can see it goes through a NOR gate which feeds directly into another NOR gate. That NOR gate outputs on pin 13 directly into pin 2, which is an input to another NOR gate. The output of this gate on pin 1 goes back into the NOR gate on pin 12, and so on and so forth. This is definitely some kind of a flip-flop, so I'm going to call it flip-flop trigger. Filling in some blanks, pin 13 of IC24 is plugged into the board and there it receives 5 volts. The NAND gate which this feeds has an output on pin 11 which is connected to pin 3 of our new IC, which is an input to one of the NOR gates which makes up our flip-flop. So we've pretty much taken all the information we can from this picture. It's time to draw a schematic. I'm going to keep the truth tables of our NAND gates and NOR gates handy because that seems to make up the entirety of this circuit. Quick point about these truth tables. Let's look at the NAND one to start with. The interesting row in this table is when A and B are both 1, we get a 0 on the output. And similarly for the NOR gate, the interesting row is when A and B are both 0, we get a 1 on the output. Let's draw a schematic, and accidentally on purpose I'm going to start looking at the inputs to the new IC on pins 5 and 6, that's A7 and read. These are both very active signals, they'll be flipping around all over the place, and the output of this NOR gate will also be flipping around all over the place. If we trace the output of this from pin 4, we can see it goes into IC24 pin 2, which is the input of a NAND gate. Let's analyse this, starting with the NOR gate. The interesting row, as I mentioned, was when both inputs are 0. So when read is 0, which means there's a read happening, and A7 is 0, we get a 1 on the output. That means we have a 1 feeding an input of our NAND gate. The interesting row in the NAND gate is when both inputs are 1. So when A7 is low and read is low, and MREC is high, we get a 0 coming out of this NAND gate. Let's call this output trigger or trigger 1. And let's explain it in words. Trigger 1. A read is happening from an address with A7 low which isn't a memory read. Or more simply, IO read A7 low. This is something that we can do with a line of code conveniently. So let's trace where does this output go to? Well, it goes to pin 12 of IC24, which is an input to another NAND gate. This NAND gate is shared with a constant plus 5 volts or a constant 1 in logic. This effectively halves our truth table as highlighted here, and we can see that whatever goes in as the trigger gets inverted on the output of this NAND gate. In fact, it probably makes more sense that we call our trigger an active low signal. So I'll put a little slash in front of it there so we know that that's the case. We can then call the output of this NAND gate TR1 active high. Now we can start drawing our flip-flop, because the output of this goes directly into the flip-flop. It's made up of two NOR gates, and they're connected together like this. If you like to pause and trace the wires around on the drawing there, you'll see that that's the case. Our trigger signal goes into one of the inputs of this lower NOR gate in the flip-flop, the output of which is our bank select, or our 1 or 0, which ultimately feeds upper RAM to select the half of the upper RAM chips which we want to use. This is indicated by an LED which is fed 5 volts, so if the bank select is 1, the LED will be off, and vice versa. If bank select is low or 0, we'll have current running through the LED and it will illuminate. I've called them bank 0 and 1 because that corresponds with the logic level of the bank select. Let's have a walk around this flip-flop and figure out how it's going to work. Let's say the bank select is currently at 1. That means our LED will be off because the voltage difference across it is pretty much 0. Let's just assume that the other input to the flip-flop up here is 0, meaning that it's receiving 0 and 1. Looking at the truth table, it will be outputting a 0. So the lower NOR gate is receiving a 0 on the top and a 0 on the bottom because we're not firing off our trigger. So everything is stable and we're happily programming away using bank 1. Now we fire off our trigger because we want to switch our upper 32 kilobytes of memory to the other page or other bank, which means we get a 1 on the lower input to this NOR gate. This flips the output to a 0, meaning that the input to the upper NOR gate switches to 0 as well, and we get a 1 on the output of this gate. This means that the input to the lower NOR gate switches to 1, and we have two 1s going into it, which doesn't change the output, it stays at 0. Now our trigger is only momentary, that switches back to 0. The output of the NOR gate that it feeds stays at 0 because the other input has now flipped to 1. By now our LED has turned on, indicating that we are now using bank 0 of the upper memory. We've paged out 32 kilobytes that we were using and paged in the other 32 kilobytes that makes up the other half of the upper memory. That's great, that tells us how we make the switch in one direction. What about the other direction? Well, we need to control this top input of the NOR gate at the top of the flip-flop. I've marked it here 1 in this case, and we can use logic to follow through that the output would become 0. We then get two 0s going into the lower NOR gate, which flips the output to 1, our bank is switched to 1, and the LED turns off. In reality, the two inputs to the flip-flop will be changing at the same time, and you can do the same kind of logic walkthrough for every case, every combination of 0s and 1s, to figure out which way the bank switches, depending on these two inputs. Let's complete our schematic so we can understand how we can use code to manipulate both of these inputs. The top NOR gate is fed by the output of another NOR gate, and there's a resistor in between the two of them for timing purposes. Our flip-flop trigger, the active low version of it, is fed into one of the inputs of this NOR gate, and the other input is populated by A14. So if we want to control the top input of the NOR gates of the flip-flop, we need to set A14 to either 1 or 0. Let's assume it's set to 1, the output of the NOR gate will always be 0 in this case, and we have the first case of the flip-flop which we walked through a minute ago. Setting it to 0 obviously has the opposite effect as long as the trigger is set. So let's put this all together. We need to figure out how to manipulate the bank. Well, we have to use A7 and A14. If we set A7 low and A14 high, we can switch from bank 1 to bank 0. And on the other hand, we can switch from bank 0 to bank 1 by setting A7 low and A14 low. Obviously, there are many addresses which satisfy these conditions, but for simplicity's sake, let's just set all the other address bits to 1. If we convert these binary values to decimal, what we get for the first case is decimal 65407, and the second case is 49023. Now we're very lucky because we do have a picture of the instructions that came with the SP80, thanks to Tynemouth software. Go check out the blog there, I'll put a link in the description. They've done a very similar thing, reverse engineering this mod. And what we see is the same values in the instructions, 65407 and 49023. Wonderful. Well, it would be wonderful if we were using in commands. An in command would set read, and as we can see from the schematic, read is one of the very first inputs to setting our trigger. There it is. Now this really boggled me for a long time. I was scratching my head for hours. I was certain that read was the correct input from what I'd seen in the pictures and from the schematic. You can see that pin 5 of IC24 is indeed read according to the schematic. And this is most certainly taken from IC24 and fed into the new IC based on the pictures that I had. Well, it turns out this is just a small mistake in the schematic, and these pins 4 and 5 going into IC24 should be swapped. Aha! This is good news because it means that we don't have read going into our circuit, we have write, or at least we have a delayed write signal. As we can see, it is split and fed into both inputs of an OR gate, and the output of that is what we're taking into our new IC on pin 6. So we need to correct our schematic a little bit. Where we have read here on the left, we're going to change it to write, which is also an active low signal. Let's also correct our drawing so it says write, and our description of our trigger so it says write. Okay, everything's in order now. So if we were to build this up, all we would have to do is write out 65407, comma, some value, we'll just put 0 because the data doesn't matter, and we would switch from bank 1 to bank 0. Similarly, we just need to write out 49023, comma 0, and we'll switch back from bank 0 to bank 1, and there we have it. That would give us 80 kilobytes of usable memory with the top 32 kilobytes switchable by paging. So how are we going to do this? Well, I'm going to hack up my own issue 2, going to build a little breadboard with this new IC on, and we're going to have a go at it ourselves. So here it is. Here's the breadboard, here's my issue 2, and I've built this up exactly as per the schematic which we just looked at. Let's give it a try. We're currently in bank 1 as the LED is off, so we have to type out 65407 0 to switch to bank 0. Let's try it, and we can see the LEDs turned on, and that means we've switched the bank. Lovely. How do we switch back? Well, out 49023 will set A7 and A14 low. Let's try it, and we should get the LED turn off. There we go, we're back to the other bank. Lovely, in theory that's working. Now let's just see if it works the other way. If I put the wrong command in now, 49023, we see that we don't switch bank. The flip-flop does not flip, nor does it flop. Let's try the other case. If I flip us back to bank 0 and we put in out 65407, we should find that nothing happens and the LED stays off, and that's exactly what happens. So it's working perfectly. Lovely. Now we can demonstrate this in a very simple way by writing a value to the upper RAM. Currently we're in bank 0. I'm going to write to address 32790, and I'm going to write the value 42. Okay, so we should have 42 written to that address in our upper memory, bank 0. Let's peek it out. So what we have to type is not just peek, Jim, that's not going to work. You need to type print peek 32790, and it will output the contents of that address in upper memory. There it is, 42. Lovely. Now we need to switch the bank back to bank 1. So how do we do that? Out 49023 should do the trick. Let's give it a go, see if the LED turns off, and indeed it does. Now we can do the same print peek command to the same memory location and we'll get a different value out. We're going to get 0. There it is. So that proves to me that we are switching banks in the upper memory, and just to be doubly clear, let's write our own value here to 32790 in bank 1. I'm going to write 24 because that's just the opposite of 42. Seems nice. There we are, 24's now gone in to that memory location in bank 1. We can check it, print peek 32790, There's 24. Now, if we switch the banks back to bank 0 without 65407, and we do the print peak command once more, we should get 42, which was the original value which we wrote in, and there it is. Well, hey, it works perfectly brilliant. So there we have an 80K spectrum, all made possible with one additional chip. Now I wanted to see this working on the logic analyzer so we can see everything that we predicted is happening as we expected. So here it is, cheap and cheerful. I bought it especially for this video. All we need to do is use these fancy little springy clip probe things. As you can see, you squeeze it and two little prongs come out like that. Ooh. And we're going to clip them onto the legs and the wires and the things that we're interested in our schematic, so we can see all the values flicking around as we expected. So I've picked a few interesting parts of the circuit, I've attached these probes to them, and I've took a little measurement. Well, let me tell you, this is fiddly and messy, and this is a fairly cheap probe. All these wires kept popping off, but I got there in the end. I hooked up everything I was interested in within the limits of the 8 channels I could measure, and managed to successfully measure something. So using this simple code which cycles between banks, switching from bank 1 to bank 0 fairly rapidly, I took a measurement and here's what I got. We can see that the bank is switching and the inverse of the bank is the inverse of the bank. Lovely. I also probed A7, read and MREC so we can see when the trigger conditions are right, and the orange one there, 2413, represents our trigger, active low. We need to zoom in a bit to see the trigger happening though, so let's go in. Now this cheap logic analyzer is a bit slow for the spectrum, and I couldn't see the trigger conditions flipping at every single bank switch. Thankfully though, we fluked this one. We can see we got only one sample of the values being set, but at least we managed to capture it. I must invest in a better logic analyzer. Anyway, let's have a look. A7 and... oh, it's still called read on here. Hang on, I'll fix that. We can see our trigger conditions all go through at the same time. A7 is low, write is low, and MREC is high. So we have an IO request where A7 is low. This sets off our trigger, active low, that's the orange line. And everything follows to the end. I couldn't probe everything, I only had 8 channels, and we see that the bank switches after one more sample, or at least one more sample at the rate of the logic analyzer. Take the timing of all this with a pinch of salt, because we're only getting 24 MHz out of the analyzer when we should be nearer 100 or 200 if we wanted to see things a bit more close to reality. Well, gosh blimey, I think I've kept you long enough, and I think if you're still with me, you should now understand how the 80K upgrade mod works, as well as how the Speccy addresses all of its memory. And if you are still with me and you followed along, you should have one burning question. How the hell is this supposed to work if we're switching to a bad half of the upper memory chips? Well, it's a bit of a gamble if you don't want to swap out all of your upper memory chips, and in all likelihood, it won't work. You might have noticed I chose a very low address in upper memory for the demonstration. That's because I have a bad half of my upper memory on this board. If you want it to work and to have a full 80K, you need to remove all of your half bad upper memory chips and replace them with fully good chips, such as 4164s, which you can get now for very cheap. When you bought this kit back in the 80s, you would have been provided with 8 upper memory chips, which are all good. And that just about concludes the video on the SP80. Thanks for sticking with me, and I'm going to tell you now, this was a stepping stone to the next video. Check this out. You might recognise this board from the Speccy groups on Facebook. Colin was kind enough to send me it so I could reverse engineer it and make a video of it. In doing so, I realised I needed to do a bit of homework, and that's where this video came from. So thanks Colin for sending me this, and I'm really looking forward to getting stuck into this and doing another excruciating video reverse engineering a ZX Spectrum 80KB memory upgrade. So thanks for watching everyone, and I'll see you in the next video.